Alright, in this example, we're going to look at how to sketch a graph of the original using what we have of the derivative. So below here, we have this graph of the derivative. So remember, we want to highlight, and I would say highlight that word that says what you have below. So here below we have the graph of the derivative, and we want to use this to sketch the graph of the original, f of x. So below I've set up a sign chart of my directions. From A to C, I'm always, since this is my derivative, A to C I'm positive. So my slope is always increasing on the original from A to C. And I keep staying positive, although I go down, I keep staying positive until I get to E. At E to G, my slope is now in the negative. Remember, that's the slope of the original is now in the negative. And then from G to H, I go positive again. So the next piece that I want to look at is the slopes at these. So from A to B, my slope of my derivative is positive. So my second derivative that I have down here from A to B is positive, which means it's concave up. From B to C, my slope is negative. So that means that it's concave down. From C to D, I have a positive slope. So from C to D, we have that positive slope. From D to F, we have a negative slope. So D to F is a negative slope. And F to H, we have a positive slope. So let's see how we can use that to graph our equation. So it can look like anything. There's not one particular graph that it could look like. It kind of could be all different graphs. But I just have to make sure I'm concave. When I start, my slope's going to be positive, and I'm going to be concave up. So to do a positive slope, I'm going to change my color here. Let's go with blue. So a positive slope, and it's concave up at B. Now at B, I'm going to continue positive, but I'm going to have a concave down slope. So now we kind of change directions until I hit C. At C, I'm still staying positive, but again, I'm going to go concave up until D. So we kind of do little half moons until D. And then from D to F, I'm going to be concave down, but at E, I'm going to change direction. So D to E, I'm still going positive, so kind of like that. And then at E, I turn, so I concave, concave, concave. E, I make that turn to a negative slope. Now my slope stays negative, but at F, I turn to concave up. So now my concavity kind of got screwed up here. Let me do this again. So at F, so I come down, 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 down. At F, I'm still going negative, but now my concavity has changed to concave up. At F to H, and at G, I'm going to change directions and go up again. So that's kind of like what our graph of our original would look like. We could shift that anywhere, but really we're looking at the concavity and the slopes. We have another one here. So right now we have the graph of the, and we'll go back to the middle slide in a moment. In this one, again, I want to write down my two different issues. So I have my f of x and my f double prime of x. And the key points that I'm going to look at is what's happening from 0 see if I can write a 0. There we go. 0, 1, 2 we have a change, 3, 4, we'll just do all the numbers, really 5.5, so we don't have to worry about 5.5, but all the way to 6. So from 0 to 1, I'm going to be positive, since that's our, from 0 to 1, we have a positive slope. From 1 to 2, we're a negative slope. From 2 to 3, we're still in the negative. 3 to 4, we're positive. And then 4 to 5, really that's 5.5. Let me add that in. 5.5 and 6. We're negative. And then positive all the way up to 6. My second derivative, from 0 to 1, the slope of my second derivative is negative. From 1 to 2, we're still negative. 2 to 3, we're now turning positive. 3 to 4, that slope is positive. 4 to 5, our slope is positive, but it's a little bit different. And 5 to 6, or 5.5 to 6, we're positive. All right, so now we're going to see how to graph this. All right, so I'm going to start with my first derivative, and it says that it's positive but concave down. So I'm going to start at 0, and I'm going to be positive, but I'm going to be concave down, and I'm going to continue concave down until I hit 2. But at 1, from 1 to 2, my slope changes to a negative slope. And then at 2, I turn to concave up, but I'm still going on a negative slope. 2 to 3, I continue negative but concave up. At 3, I turn concave up and a positive slope. But hold on, at 4, I'm still concave up by my negative slope, and I know that there's an issue here at 4. So something that's not differentiable at 4, and we know our things that aren't differentiable are cusps, corners, and vertical asymptotes. So if I say that it's continuous, I could make it, let's make it into a corner, or a cusp. And I can make it into a cusp, so I can stay that concave up, but now with a negative slope. So a negative slope, but concave up. And then I'm going to turn and I'm going to swing back up again, positive, positive at 5.5. So what I drew here was a cusp where it's not differentiable, but we can make it continuous. All right, so that's something that we see here that is a way to kind of look at a graph and draw. So this would be f of x. All right, so the last bit that we have in here is to sketch the graph of f of x when it's equal to, sketch the graph of f of x is equal to z squared over, or we could say that's x squared over x minus 2 in the domain of all reals except 2. So we're going to do this one as a class, but one of the things I want you to think about as we do this is we need to find critical values for f prime of x, what that's equal to, and f double prime of x. And so this is a great one to come back and practice to and see how well you can do it sketching a graph like this after we've done it together.